And in third day of the conference, again, first talk is of Professor R. Balasubramanian. It's my pleasure to introduce him in front of you, even though on the first day, many times introduced by different dignitaries. During the inauguration, Professor K.C. Sinha and others have been introduced. Then in his first keynote, introduced by Professor Piyush Chandra. And it's my pleasure to say something about Professor R. Balasubramanian, Padma Shri R. Balasubramanian. May you can knowing about the candidates for Bhatnagar Awardee. Before 45 years, scientists have been getting that award, and he is one of the awardee of Bhatnagar Awardee, Professor R. Balasubramanian. Even though he is of more than 73 years, but before time, I think at 9:05, he was ready and waiting for the vehicle to come at the time, and later and program will go accordingly, what's the schedule is. He has many contributions in number theory as well as in algebraic number theory, and I am fortunate that 2 or 3 theses of my students evaluated by him. So with this brief note, and of course whatever he has discussed in his first lecture, just continuing it, I am going to show something about the number theory and what's the related area in which people can work in future too. So with these words, I would like to invite Professor R. Balasubramanian for his talk.
Since I was not feeling well, I could not give the lecture yesterday. Today I am giving the lecture. Okay. Again, let me continue on number theory. See, number theory has many aspects. One studies about prime numbers, that's one aspect. Some transcendental number theory. Then additives, meaning essentially writing an integer as a sum of integers of a special type. And for example, most of you would have known about the Goldbach's conjecture. Goldbach's conjecture is the statement that every even number can be written as sum of 2 prime numbers. And this Goldbach's conjecture is still not solved yet. And there is another aspect of additive combinatorics, another aspect of number theory, which I have come in the recent past, maybe in the last 20 years, which is called additive combinatorics. That is, doing combinatorics in number theory. This has many aspects, and there is something called the Ramsey theory, and I will just introduce something like the Ramsey theory, but probably I won't talk much about that, and then some free sets. That's all. What is Ramsey theory? Operate this. So if you move, there it moves, right. Oh, page up page. Okay. Okay, fine. Yeah, first of all, what is Ramsey theory? Ramsey theory says the following: you have all the integers, and when you look at all the integers, they have some property. But now you don't take all the integers, you take the integers and color them with some 3 colors, blue, green and yellow. And then whatever properties that all the integers have, can you find within the blue color alone or within the green color alone? Okay? Therefore, if you can find out a property within one single color, that property is called a monochromatic. Therefore, mostly what you would be interested is, there are many equations which can be solved in integers, and now we are asking whether they will have a monochromatic solutions, which means that if you take all the integers and color them, whether the equation will still have a solution in one single color. That's exactly what is that. We illustrate this by means of what is called Schur's theorem. Therefore, the Schur's theorem says the following: let R be a natural number, then there exists a natural number capital N, which depends upon R, such that the following holds. What does it say? It says that if you look at this equation x plus y equal to z, and then x plus y equal to z has of course a solution in integers. You can write a lot of solutions, 2 plus 3 equal to 5, 7 plus 9 equal to 16 and so on. But on the other hand, now what I am asking is that if we take all the integers and color them, therefore the 1 will be colored blue, 2 will be colored green, 3 will be colored yellow and 7 will be colored blue. The 3 colors I am giving. And now I want a solution for this equation x plus y equal to z, where x, y, z all belong to the same color. Therefore, if x, y, z, everything should be green or everything should be blue. And if that happens, then it is called a monochromatic solutions. And the first result in this direction was proved by Schur, and Schur proved that if you look at this equation x plus y equal to z, then this equation does have a monochromatic solution. Which means that whichever way you color the integers, and you should take only finitely many colors, but then you can take as many colors as you want. You can take some 250 colors and then color them any way you want. Even then, this particular equation x plus y equal to z will have a monochromatic solution. That's where the whole thing started. And in fact, the reason why Schur did it, I won't go into the proof details, but the reason why Schur did it is there is something called a local global principle in number theory. For example, you have an equation and then you want to know whether that equation has an integer solution. If you want to know that the equation has an integer solution, then it should definitely have a solution modulo p. Because if 7, 23, 47 is a solution in integers, the 7, 23, 47 will also be a solution modulo p. Okay? Therefore, if there is any solution, there will be a solution modulo p. Now something called the local global principle says that if you have a solution modulo p for every p, does it really mean that it will have a solution in integers? Okay, and that is one important question which is discussed in a number of things, but I won't go into that. And somehow that is exactly what Schur wanted to prove. Schur wanted to prove that given any n, there will be some modulo p for which this equation x power n plus y power n equal to z power n, modulo p will not have a solution, and therefore you will conclude Fermat's last theorem. Okay, I wonder how many of you have not heard Fermat's last theorem? Is Fermat's last theorem a familiar name for all of you? Okay, can I assume that? Okay. Therefore, he wanted to prove Fermat's last theorem, and therefore he wanted to prove that the Fermat's last theorem does not have a local solution, and therefore he wanted to know that if you take an nth power and add another nth power, whether it can be an nth power modulo p. And unfortunately, he proved that the Fermat's last theorem cannot be proved by that way, because whatever attempted he made, that failed. But in order to do that is what he should prove his theorem. Okay, and this is a proof. I don't think I have time for that. Okay, but now the next question is, Randolph's theorem, etc. Probably I will skip. And now the question is L dash. Yeah, this is the important thing. Now the question is, now we are going to ask a question not about x plus y equal to z, but about the question x plus y equal to 2z. Therefore, now you are asking whether there is a monochromatic solution for this equation x plus y equal to 2z. Of course, x plus y equal to 2z has a lot of solutions in integers. For example, 3 plus y equal to 2 times 4, 7 plus 13 equal to 2 times 10, and so on and so forth. But now you are asking, but if on the other hand, if I take all the integers and finitely color them, if I color finitely many integers, if I color the integers finitely many, but I did not even take all the integers. I take integers up to a large level, from 1 to n. I take integers up to 1 to n, and then finitely color, and then is it necessarily true that this equation x plus y equal to 2z will have a solution? Okay, I will say something about this now, and then I will come back to this x plus y equal to z a little later. Now you see, if this x plus y equal to 2z has a solution, that means the numbers x, z and y are in an arithmetic progression. Therefore, you are now asking the simpler question, namely that if you have if you take the integers and then color them finitely many, then is it necessary that is at least one color will have a 3-term arithmetic progression? That's the question you are asking. Okay, therefore I take the integers and color them, and I want to know whether they will have a 3-term arithmetic progression. And in this particular thing, L dash conjecture, no, it was already proved by Van der Waals. Van der Waals proved that if you take it and then a 3-term arithmetic progression will be there. But there is a difference between Schur's theorem and Van der Waals theorem. The Schur's theorem, you know that there is a solution, but it is not necessarily true that that box which contains the maximum number of elements will have a solution. The solution may be in a box which contains a smaller number of elements. But in Van der Waals theorem, L dash conjecture that the box which contains the maximum number of elements will have a solution. In other words, if you take the integers 1 to n and you take a subset A, and provided this A has a positive density, which means that this A is bigger than alpha times n for some fixed alpha. Therefore, you cannot take a small set, but take a big set. The big set should have at least n over 2 elements, or n over 10 elements, or n over 57 elements. Okay? Therefore, it should have a positive density. And therefore, if the A has to be bigger than alpha times n, if A has a bigger than alpha times n, then it has an arithmetic progression of 3 terms. And in fact, L dash went further. L dash went further that not only it will have an arithmetic progression of 3 terms, it will have an arithmetic progression of any number of terms you want. Therefore, you take a set A such that mod A is bigger than alpha n, and of course I am assuming that the capital N is sufficiently large, and if the capital N is sufficiently large, and if you take a subset A which is bigger than alpha times n, then this set A will have an arithmetic progression of some 378 terms. You can even fix how many terms you want. Okay. You can fix that I want an arithmetic progression of 1023 terms. Then is that if, and this alpha again you can fix very small. Alpha can be something like a 1 over 1000. Therefore, if you take a set A contained in N, which is cardinality of A bigger than 1 over 1000 times N, then this A will contain an arithmetic progression of 1023 terms. Just needs a positive property, which is definitely not true for Humphrey. And if I have a Humphrey set, then it is not necessarily, okay, anyway I will come to that a little later. Okay, now this is the interesting, this conjecture turned out to be one of the very important conjectures, and this more or less started the study of this additive combinatorics. This conjecture was proved by for k is equal to 3 by K.F. Roth in 1953. Okay, and he used what is called a circle method, which I did explain yesterday, namely a method which was developed by Hardy and Ramachandran to study partition functions. And using that, he proved that if the cardinality of A is bigger than alpha times n, it will have a 3-term arithmetic proportion. Then k equal to 4 was proved by Sammardi. Sammardi, as most of you would have known, was a great combinatorics person, and he proved in 1969. And Roth again proved the same thing in 1972 by his circle method. And the general case was proved again by Sammardi, and the method is combinatorics. I mean, Sammardi's proof was called a masterpiece of combinatorial reasoning by L-. It is a very, very difficult proof. But because this theorem is very important, then many people try to give other proofs, not necessarily using combinatorics. And the proof came from Furstenberg in 1977, and he used what is called the ergodic theory. And then Gowers proved in 2001 using Fourier analysis, and the results related to K approximate group, about which we will talk later. And of course, Gowers did a lot. I mean, Gowers is one of the big names here, and he introduced the Gauss norm, which has been important for many purposes. And now let me define what is an approximate group. What is an approximate group? Suppose G is a abelian group and A is okay. And suppose I take a subgroup H and a subset A of a coset. Then when you add two cosets of a subgroup, then you will get a third coset. Okay, which means that the cardinality of A plus the cardinality of A will be the cardinality of A plus A will be the same as cardinality of A, because A is a coset and I take one coset, let us say 3 modulo 7, and I take another coset 5 modulo 7, and then when I add 3 modulo 7 and 5 modulo 7, for example, I will get the full 1 modulo 7, and therefore A is there in A 3 modulo 7, then A plus A will be there, essentially because that is an idea of a subgroup. A plus A will be equal to A. And a K approximate subgroup means, first of all, let's say G be a commutative abelian group, and consequently we write the group operation additively. Therefore, our group operation is additive. Therefore, our group operation is plus. And if G is a commutative abelian group and A is a finite set, then we say that A is a K approximate subgroup if cardinality of A plus A is less than or equal to K times cardinality of A, which means that when you take the A and another A and add A plus A, okay, let me explain what is A plus A means. A plus A means you take an A1 from A, A2 from A, and add A1 plus A2, keep doing it for every pair, but then sum of the A1, A2 can apply many times, multiple times, okay, but you look at it as only as a set, which means that if it appears many times, then you take it only once. Okay? Therefore, A plus A, yes, which we have defined. Therefore, A plus A can be defined as those elements of the group where G can be written as A1 plus A2, where A1 is an element of A and A2 is an element of A. Remember, the point is the same G can be written as, may be written as A1 plus A2 more than one time. Probably you can write G as A1 plus A2 7 times. Which is, of course, you don't count the G 7 times, you count the G only once. You view it only as a set. Therefore, only view as a set, then the A plus A, the cardinality will go down, because many elements may have multiple representations, and then the representation will go down. And after that, if A plus A is only up to a constant times capital A, then it is called an approximate. Now there are questions about approximate groups which I won't bother about. Yeah. Now ask the question. I don't even need to yell free. Yes. Okay. Now one can ask the question. A sum free set. This is the question: X plus Y equal to Z. Therefore, when I say a set is sum free, that means this equation X plus Y equal to Z does not have a solution. That is equivalent to say that x plus y equal to z does not have a solution is equivalent to saying that if you take a plus a and another a and intersect, the intercept is empty. That is what summary means. A plus a intersection a is empty. And you can of course define L3. L3 is a1 plus a plus a L times intersection a should be empty. That is called L3. And not much is known about L3, therefore we are only talking about the subpresets. Therefore now we are only asking subpreset, which means that L equal to 2, therefore I am only asking, I have a finite abelian group G, and once I have a finite abelian group G which is written additively, therefore addition is a group operation, therefore, and then I take a set A and then add A to A, then you have an A plus A, and I want A plus A to have a empty intersection with A, which means that no element of A can be written as A1 plus A2. If no element of A can be written as A1 plus A2, that is called a summary. That is exactly the equation which you originally saw, x plus y equal to z. And now one can say something. Suppose you take 1 to n, and in 1 to n you take odd integers. Odd integers are nearly n over 2. If the odd integers are nearly n over 2, still they do 78 terms. You can even fix how many terms you want. Okay. You can fix that I want an arithmetic progression of 1023 terms. Then is that if, and this alpha again you can fix very small. Alpha can be something like a 1 over 1000. Therefore, if you take a set A contained in N, which is cardinality of A bigger than 1 over 1000 times N, then this A will contain an arithmetic progression of 1023 terms. Just needs a positive property, which is definitely not true for something. And if I have a summary set, then it is not necessarily, okay, anyway I'll come to that a little later. Okay. Now, this is an interesting, this conjecture turned out to be one of the very important conjectures, and this more or less started the study of this additive combinatorics. This conjecture was proved by, for k is equal to 3 by K.F. Roth in 1953. Okay, and he used what is called a circle method, which I did explain yesterday, namely a method which was developed by Hardy and Ramanujan to study partition functions. And using that, he proved that if the cardinality of A is bigger than alpha times n, it will have a 3-term arithmetic property. Then k equal to 4 was proved by Semeridi. Semeridi, as most of you would have known, was a great combinatorics person, and he proved in 1969. And Roth again proved the same thing in 1972 by his circle method. And the general case was proved again by Semeridi, and the method is combinatorics. I mean, Semeridi's proof was called a masterpiece of combinatorial reasoning by L'. It is a very, very difficult proof. But because this theorem is very important, then many people try to give other proofs, not necessarily using combinatorics. And the proof came from Furstenberg in 1977, and he used what is called the ergodic theory. And then Gowers proved in 2001 using Fourier analysis, and the result related to K approximate group, about which we will talk later. And of course, Gowers did a lot. I mean, Gowers is one of the big names here, and he introduced the Gauss norm, which has been important for many purposes. And now let me define what is an approximate group. What is an approximate group? Suppose G is a abelian group and A is okay. And suppose I take a subgroup H and a subset A of a coset. Then when you add two cosets of a subgroup, then you will get a third coset. Okay, which means that the cardinality of A plus the cardinality of A will be the cardinality of A plus A will be the same as cardinality of A, because A is a coset, and I take one coset, let us say 3 modulo 7, and I take another coset 5 modulo 7, and then when I add 3 modulo 7 and 5 modulo 7, for example, I will get the full 1 modulo 7. and therefore A is there in A 3 mod of 7, then A plus A will be there, essentially because that's an idea of a subgroup. A plus A will be equal to A. And a K approximate subgroup means, first of all, let's say this G be a commutative abelian group, and consequently we write the group operation additively. Therefore, our group operation is additive. Therefore, our group operation is plus. And if G is a commutative abelian group and A is a finite set, then we say that A is a K approximate subgroup if coordinate of A plus A is less than or equal to K times coordinate of A. Which means that when you take the A and another A and add A plus A, okay, let me explain what is A plus A means. A plus A means you take an A1 from A, A2 from A, and add A1 plus A2. Keep doing it for every pair. But then sum of the A1, A2 can apply many times, multiple times. Okay? But you look at it as only as a set, which means that if it appears many times, then you take it only once. Okay? Therefore, A plus A, yes, which we have defined. Therefore, A plus A can be defined as those elements of the group where G can be written as A1 plus A2, where A1 is an element of A and A2 is an element of A. Remember, the point is the same G can be written as, may be written as A1 plus A2 more than one time. Probably you can write G as A1 plus A2 7 times. The thing is, of course, you don't count the G 7 times, you count the G only once. You view it only as a set. Therefore, only view as a set, then the A plus A, the cardinality will go down. Because many elements may have multiple representations, and then the representation will go down. And after that, if A plus A is only up to a constant times capital A, then it is called an approximate group. Now there are questions about approximate groups which I won't bother about. Yeah. Now ask the question. I don't even need to L3. Yes. Okay. Now one can ask the question, sum free set. This is the question, express Y equal to Z. Therefore, when I say a set is sum free, that means this equation express Y equal to Z does not have a solution. That is equivalent to say that express Y equal to Z does not have a solution is equivalent to saying that if you take A plus A and another A and intersect, the intersection is empty. That is what sum free means. A plus A intersection A is empty. And you can of course define L3. L3 is A1 plus A plus A plus A L times intersection A should be empty. That is called L3. And not much is known about L3, therefore we are only talking about the sum free sets. Therefore, now we are only asking sum free set, which means that L equal to 2. Therefore, I am only asking, I have a finite abelian group G, and once I have a finite abelian group G which is written additively, therefore addition is a group operation, therefore, and then I take a set A and then add A to A, then you have an A plus A, and I want A plus A to have a empty intersection with A, which means that no element of A can be written as A1 plus A2. If no element of A can be written as A1 plus A2, that is called a sum. That is exactly the equation which you originally saw, express Y equal to Z. And now one can say something. Suppose you take 1 to n, and in 1 to n you take odd integers. Odd integers are nearly n over 2. If the odd integers are nearly n over 2, still they do. Which of course was not the case for an arithmetic progression. Arithmetic progression says if the cardinality of A is bigger than alpha times n for any alpha which is positive, then already it will have a solution. But that is not true for sum free set. Even up to the density half, you may have sets which do not have a solution. Now the same question, the sum free sets we are asking for finite abelian group. That sum free set A, and I want to know what can I say about the sum free set A. Therefore, what is the cardinality of the sum free set? Okay. These are the questions which we are related. Okay. Now the answer to this question seem to depend upon the order of the group G. And if the order of the group G, therefore we say that G is a group of type 3, the question becomes somewhat more difficult. The type 2, the G is divisible by, order of G is divisible by 3. Those two types are easy. And in fact, the first two questions, what is the cardinality, what is the classification, that was provided by Dayananda and Yap. Is not type 3 a complete answer. Till 2005, the answer to the first question of type 3 groups was known only in a very special cases. Okay, G is of type 3 as we defined if all the divisors of its order are congruent to 1 modulo 3. If all the divisors are congruent to 1 modulo 3, it's determined to the, and then you have two subgroup H and K. And now let us assume that the two subgroup H and K are isomorphic. Then you would like to know whether there is an automorphism of G which is restricted to H gives you K. In other words, if there are two isomorphic subgroups, whether this isomorphism can be extended to an automorphism of a full group. And that is a question called a Burnett question, which has not been solved completely, even in the case of the finite abelian group, and that's where we have a problem in really solving the question completely. And with that, I think I will stop it.
So thank you so much, sir. Any quick questions you can ask within a minute, please, so that we can go for the next. Yes, please.
Sir, in number system, I write cardinal number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Why 10 is a row of single digit? 10 is a stand in single digit.
10 is not single digit, yeah.
Yes. 1 to, I know 1 to 9 as single digit.
Yeah.
But it's row vertically. Why 10 stand there?
Oh, why is not single digit? That's an interesting question. Okay, let's answer that.
There are many questions, right?
Throughout the world, by different, okay, I can even use this. The number system was developed throughout the world by different civilizations. And the different civilizations came to the representation of numbers in various symbols. Okay? And let me talk about something which is not related to, which is essentially the Roman symbols. Okay? In the Roman symbols, there is no question of why 2 digits, etc. What they did was, if they wanted to write 573, they created a symbol for 500. Okay. They created a symbol for 50. They created a symbol for 10, which all of you know is X. They created a symbol for 1, which all of you know is 1. Therefore, 573 would be written as 500. I think, what is that? D plus 50 is L plus 20, which is X plus X, plus 3, which is I plus I plus I. This is how they wrote the numbers. Okay? This, as you can see, has many problems. Okay? Number 1, then if you want to write a bigger number, okay, like 1,78,493, then you should now create a symbol for 5,000, create a symbol for 10,000, create a symbol for 50,000, create a symbol for 1 lakh, and so on. You can write it. And now you can imagine, if you write numbers like that, and if you want to add 2 numbers, okay, there's absolutely no way you can do it. No? If I now tell you CBXYI plus DMDXIII, what is the sum? It's not something which you can ever do. Okay? Therefore, this system of creating a symbol for each one has its own disadvantages. Okay? By on the other hand, the Indians developed something called the decimal system. Okay? This decimal system involves a zero. Okay? And of course, now we know that probably the Indians were not the only people who did it, and the Chinese also did it, and so on and so forth, but essentially it is attributed to India. Okay? And there, once you write the decimal system, which means that you can have only the whole idea is you have only finite number of digits. Okay? Therefore, you don't have one digit for 1 and 1 for 5, 1 for 10, 1 for 50, 1 for etc. But you have only 9 digits, which is exactly, if you are using computer, you only 2 digits, 0 and 1. And then try to write every number in terms of only those 2-3 digits by using again the positional advantage, where you are putting 573 is not the same as 375. Okay? Whereas V111 is the same as 111V, because that's all what you are doing. Okay? Therefore, with the limited number of digits, if you have to write all the integers, there is no way you can essentially do it with only 1 digits. If you write 1 digits and you want to write up to 1 lakh, then you need 1 lakh symbols. We don't want to do that. Therefore, somewhere you have to go to a 2-digit number. Where you go to 2-digit number is called the base. If you write 1, 2, 3 of 9 up, and then 10 as a 2-digit number, it's called a base 10. If you write 0, 1 and then immediately 1, 0, that's a binary. 0, 1, 2 and then for 1, 0, 0 is base 3. That's how to do.
Thank you. Any other questions, please?
Yeah, I think he wants one.
Yeah.
Order of the group can be 0 or no.
Sorry?
Order of the group.
Can be 0 or no. Group
In
का
order, you see,
हो सकता है.
once you have a group G, at least you have one element. When you define a group G, you don't have a group G with no element at all. I mean, that group doesn't make sense.
That should be non-empty, no?
Yes, the group has to be non-empty. But you can have one element.
Non-empty.
स्टार्ट में होता है सर निम्न सर
Yes.
तो स्टार्ट में है ना
Thanks. Any other questions? I think one questions I have already taken. Rest question you will ask outside the room. Thank you so much, sir. Thank you so much, Professor Padma Shri R. Balasubramanian, for his nice talk. And he has given flavor of many branches of number. He encourages to all of us to work in future. So thank you so much once again, sir. Now please take your seat, please.